So in this section we look at solving linear ordinary differential equations, pretty much just called linear equations in the context of this course. But yeah, these are linear differential equations pretty much, and we are dealing with first order ones in particular here. And the book says to do this. Like, this is basically almost a pure copy for the most part from the book of how they say you should do it. I mean, you'll see, but I think it's easier when it's done in practice. It's a lot easier to understand what you should remember and what you shouldn't. But you don't need to worry about it, I mean. But yeah, they claim you rewrite it as x prime minus ax equals f. You can also just leave it at x leave it or rewrite it as x prime equals ax plus f, depending on the circumstance. It's the form of the equation though, where it's basically the term a times x plus the term f basically, and x prime is equal to it. This is what generally is called as a linear equation. The standard form, I'm pretty sure, is called this one, just off the top. Proper term. And how to, but that's not important. What's important is being able to solve these though. The integrating factor is a e to the negative integral a t dt. Basically, that's why you want to know what your a t is, which is a term here, and your f. Because in the end, you get stuff like this, but this stuff is basically, you do solve this, we have xt equals this divided by u or t. So you'll see, but basically that's what you need to really know, is how to get u or t in this formula here. But that'll make sense in a moment when we see an examples, several of them. Variation of parameters is another method that we won't do as much of, mainly because I find that it takes longer almost. Like in many cases, it seems to take longer to do or at least there's more technical work you have to do. And generally speaking, it seems like it's just a lot more easier to focus primarily on one method and just know how to do the other one if you're ever asked to do both. Like, you could be asked to do the same problem twice on a test. So to be very comfortable with, I prefer being comfortable with integrating factor, because it just, it's, as long as you remember one or two, like a couple things about it, it's, I think, a little bit more straightforward to remembering it. But yeah, various parameters though claims all these steps, but you'll see, this is technically what the book would say. I think seeing it is more important. But that long introduction out of the way. Let's start. So in 1 through 6 we find just the general solution of the first order linear equation. Y prime plus y equals 2 is a very basic one we'll start with. And in this case we have x prime minus ax equals so I tried to solve it by putting it into that form, like trying to follow a little bit more strictly a guideline, but in the end I caved into it my way anyway, but I started off. So basically I say that a at t is equal to -1, like -1 times y, and f equals 2 right here. You could rewrite this, and I'll do another one, but y prime equals -y plus 2, and you'd see that a at t is -1. But the integrating factor is just e raised to the power negative integral of a at t dt, so it's -1 here, so it's literally just, it's basically just the integral of t and of dt, I mean. So it becomes just t. So e to the t, that's where u or t is, and we know what f term is, it's just 2. So what's important here is y at t here, y at t, because it's y prime and y we want to know. What y at t is. It's equal to the integral u or t, f or t, dt, so the product of u or t and f or t. You know that, and divided by u or t. So this is basically how you do it. Do this over and over again for a lot of these. So the integration is like integration before. It's just integral et dt in this case, so it's just et plus c in the end. And of course 2 times a constant is going to be just a constant again, so it's 2 times et plus c. So you multiply 2 into them, divide by et, and in the end e at t cancels out on one part of it at least, so you get y at t equal to 2 plus c times e to the negative t power, because it's c divided. We can split it up and it's c divided by e at t, e to the t power. I mean, yeah, e raised to t. So you can rewrite that as constant c times e to the negative t power, because that's how you can rewrite exponentials. But that's what it is. Y at t equals 2 plus c times e to negative t is the answer. That's a general solution. And I'm going to show you this case without even being asked to show you the other method. But for this method, mainly you need to worry about is these two formulas, and you'll be able to solve an equation as long as you can integrate properly from there. Integral u at t ft dt divided by u at t, and u at t, of course, is just very basic. Just, Gif said. And there's plenty of examples. So in this one, it's y prime. So I rewrote it as y prime equals -1 times y plus 2 to make it more obvious here. You can see a at t equals -1 and f t equals 2. And I labeled a little. So that's our first equation. -1y plus 2 is equal to y prime. So y, the homogeneous, we're basically doing it as a homogeneous solution. We're trying to show, like, so we have y prime equals -1 times y just by itself. We get rid of the f term basically, and we essentially solve this like it's a separable equation pretty much, especially in this case. dy dt equals -y is all it is. So it's integral of dy over y equals negative integral of dt. So you get natural log in it. Same process before. I'm not going to try to make this an hour long. I'm not trying to spend hours on this again. But in the end, you get the homogeneous solution using the same method as the previous section, the separable equation. We plug 2 into 1. So this is the point where it becomes, so variation of parameters is kind of what we're getting into at this point soon. So we have y, so we have a constant here. We have c, and we put it in terms of t. Like e to the c became constant c, but it's of t. C of t. So the constant in terms of t. We're making it sort of like a function, if you will. So we plug this into 1 here. So yh, we differentiate basically this. That's why I put a apostrophe there. We're differentiating this, so y prime, so this thing prime, equation here, equals -1 times, in pink, the same thing, plus 2, the f term. You see I plugged 2 into 1. Yeah, there's a lot more to pay. You have to be really careful with these because there's a lot of stuff going on. Just be very careful whenever you do variation parameters, and stuff will cancel out usually quite often as you go through it. Like here, you have your left and right hand side of the equality. We have this term cancel out on both sides. So you're left with c prime of t times e to the negative t equals 2. Yeah, and that's part of it. So make this clear this time. When you differentiated this, that's the function c at t and e at t, e to the negative t. It's a product. So it's a product of, neither one of these are treated as constants. So you have to do product rule, which is c prime of t times e to the negative t, so the original times a derivative, plus the other one's derivative times the original. That's why it's adding, and you add. So it's negative e to negative t, because derivative of e to negative t is -1, the derivative is. It's just the derivative of negative t times it, so original statement. And that's multiplied by c at t. And on this side you had negative e to the negative t times c at t, so that's why they canceled out. Just to make that clear, product rule happens, I think, pretty often when you do this. I think that's actually not an uncommon thing to have these special rules come into play. So, and then you just divide to get c prime of t by itself. So it's 2 divided by e to the negative t power would just be 2 times e to the t, because you can bring it up and switch the sign. So And then you integrate both sides with dt, of course. And it becomes 2et plus c. So it's, and then that's our third thing, so number 3 here. So we plug 3 into 2 here. And we have c at t. And we just ignore the h thing. So it's y equals 2e to the t plus c in green. And everything in pink is this equation 2 here. Times e to negative d. So yeah, so we just cancel out terms and simplify. So it's 2 plus c times e to negative t, like the other one got us. You see what I mean? It is a little bit more messy at times, even in a simple problem like this. And I don't think there's a case where I think you can, in any case where one of these works, the other one will work pretty much. It's just, there might be a case where variation parameters does actually work easier, but I really don't see it. But that's in my experience. I think that, integrating factor is a lot more straight to the point. This one, variation of parameters, we're kind of going through another step in between, if you will. Okay, but that's it for that one. So that's the first one, just that simple one split into 2 different ways you can do it. We're going to do integrating factor for most of these though, because it's just, I think, better. It's a better method, I think. So y prime minus 3y equals 5, I rewrite into y prime equals 3y plus 5, and I do this for all of them from now on. So, because a at t is literally just ripped out of it when you have it in this equality form. And I state that every time, and these go on like this. This one's straightforward, it's just e to the negative 3t, the integrating factor, and then you plug into the thing. When you do integration here, we had to do u substitution. Now, I think I get better at this, but you probably shouldn't use u substitution, because we have u at t. So just make this like v in your mind if you were to do this one. I'd make it v or another letter. Any unused letter, just make it that, and it's just supposed to be more for your own. It's just to make sure you keep things straight more than anything above all else. These little substitution steps. Everything does not, you don't mess up when doing these integration. But we do that because of the fact that I'm showing it down here and below in orange, basically to work here. But at first I showed it why we got e to the negative 3t divided by negative 3 plus c. Why is that the case? Well, yeah. Because it's e to the u divided by 3 plus c, where u equals negative 3t. I mean, they'll get better, but like sometimes, you don't think ahead of time when you do these, but at this point, it's just simple integration by u substitution. And the reason we do this is because we only have a formula for e to the u, like when it's a single thing, That's how the general formula of integration works. So we do this to keep in that form. But after that point, you just simplify down using our rules of algebra, and you get the answer down and below. This is just solving though, so they're not all wordy like the previous section was. Y prime plus 2 divided by x times y is equal to cosine x divided by x squared. Well, this time it's in terms of y and x. Y prime being a thing, so we're solving for y still, but we just have x instead of t, like in the previous, So you just get y prime by itself and solve from there. Again, just the prime, the variable is prime on it by itself. And it's the same process. We have negative 2 divided by x, so a of x, and we make e to the integral of that. What's interesting this time is that we eventually get u at t equals e to the 2 raised to the 2 ln absolute value x. And we basically put the power of absolute value x, we make it absolute value x squared, so we can cancel out e to the ln. But it becomes e to the ln x squared, so the parentheses can be, the absolute value brackets can be dropped because anything squared will be positive. So it just becomes x squared after we simplify down. And this one is a very easy integral to solve because when you do the actual plug-in for everything, because of f of x being cosine x divided by x squared, and u of x in this case, you have u of x. Make sure you do that. U of x, based on whatever variable, if you want to be proper, is x squared, so the x squareds cancel out, and it just gets integral of cosine x dx, which is just sine of x plus c divided by x squared, and I think that's good enough. There's no reason in simplifying any further from there. That was an easy one. So we have y prime plus 2 plus y equals 5t. In this case, oh wait, no, that's a t. Plus 2t y equals 1. So we subtract negative 2ty on both sides to get y prime by itself. Then we have negative 2t as our a of t. When we do integration, it's 2 times the integral t dt. So that's 2t squared times 1/2 and then so it's just e to the t squared. Plug it in. Oh, well, we have et squared times 5t dt for our integral. Put in, and we actually are trying to solve for yt, so. And this time I did v substitution instead of u substitution, just to keep things separate. Same principle though, exactly the same. So v is equal to t squared. With exponentials, you basically, whenever that's an integral, a lot of times, unless there's another exponential somehow, like if it's just one of them, you want to get that to be e raised to the power of vu or whatever symbol you're using. You want it to be a simple thing. That's at least the first thing to look for in a case like this. So dv equals 2t dt, and then you go from there, you solve for dt, and then you basically get everything set up from there. It eventually simplifies down to just 5/2 et squared plus c. And then you simplify down. You get your answer down here. 5/2 plus c times e to the negative t squared. In this one, we do x prime minus 2x divided by t plus 1 equals t plus 1 squared. In this one, the expression, of course, is t plus 1 squared. So we again just isolate x prime, and then we go from there. So t divided by t plus 1 is obviously the a of t when we have it in this form. And f of t is just t plus 1, the expression squared. So I'm going to go over here. What we have is we have negative 2 times ln of t plus 1. We integrate real quickly. This is shown in the red, but when you integrate this, it's a natural log 1 again, so t plus 1. So we have negative 2 times ln of that basically is what our e raised to. Well, we want to cancel out this natural log if we can, so we basically put the negative 2 above, and that cancels out the absolute value, since it's 1 over t plus 1 squared, so we can cancel out the natural log. The absolute value. And the natural log is cancelled by being e raised to ln of something. And this will benefit when we do it because due to the process of x of t solving for it, because we have f of t, which is t plus 1 squared, multiplied by u of t, which is 1 divided by t plus 1, which is squared. You cancel out, and you just have integral of dt, which is just t plus c, and it's divided by, of course, u of t, which was this expression, and we simplify from there. It's basically, in this case, it's t divided by 1 divided by t plus 1 squared, so it becomes t plus 1 squared times t, and c divided by that, so it's c times 1 plus t squared. That's how I got to this configuration of it. Number 6 is just, it's t times x prime equals 4x plus t to the 4th power, so we divide by t on both sides. So it's 4 divided by t is our a term, and f term is t cubed. Same process before, we have natural log of t. raise it to the negative fourth power, and that cancels out the absolute value in the end because it will be 1 divided by t to the fourth. When you raise something to an even power, it cancels out the absolute value, if there is an absolute value, that is. And we have 1 divided by t fourths times t cubed, so t cubed gets canceled, it just becomes 1 over t. You simplify down. So it's natural log of t absolute value plus c divided by 1 over t fourths. And you just do the, again, you simplify by dividing both ln t and c by 1 divided by t fourths. Basically, you divide the terms out and you get the expression. It's c times t to the fourth because we're dividing by a fraction, so you multiply by the reciprocal, which is t to the fourth divided by 1, so it's just t to the fourth basically multiplied. But nothing crazy. Okay, now it's time to do initial value problems. So we basically get a general solutions and we solve for the initial conditions, like we've done before with the separable functions specifically. So we start off with y prime equals y plus 2x e to the 2x, and we have y0 equals 3. There's an imperable, I state what we know. So a is just 1, and f term is 2x e to the 2x. So f term is a little bit bigger this time, as you might expect. Well, the integrating factor really couldn't be much more simpler than this. It's just e to the negative x. The integration is very basic. And then you plug this into a formula. And we see e to the negative x times 2x e to the 2x dx. And I basically divide. I basically rewrite it so it's easier to tell what gets cancelled. I even put e to the 2x is equal to e to the x times e to the x because when you multiply, you add, so it's e to the x plus x, which would be 2x. So I can, by using my algebra skills, and it's all divided by e to the x, so this multiplication becomes just x e to the x dx. So we have to integrate this. And I made a special note. So we have to do integration by parts. So the general idea is integral of v dw equals vw minus integral w dv. We have to label what these terms are. So v is equal to x and dv is equal to dx. Pretty obvious, like the derivative of v equals x. Derivatives on both sides would be dv equals dx. And it's integral of v dw, so we get v and dw from the expression x e to the x. So v is equal to x, so dw is equal to e to the x dx. Because that's what's remaining basically. So we integrate both sides, so integral dw and integral e to the x dx, so we get w equal to e to the x. And we plug this into the formula, so integral x e to the x dx equals x e to the x, because it's vw, so x times e to the x minus integral of e to the x dx. Because that's wdv. And we can integrate e to the x dx because it's just e to the x plus the constant c. So that's how it works. And then I can divide out e to the x, like make it e to the x times x minus 1 plus c. And that's what we plug in. So y of x is equal to 2 times, in brackets, e to the x times x minus 1 plus c, all divided by e to the negative x. So then from there, it's not looking simple, but we just have to simplify a little. So y of x is equal to e to the x times, because we basically divide out an e to the x. Show what do I do? Oh, I see. Okay, so when you divide by e to the negative x, we're going to multiply e to the x is the equivalent of that by dividing by e to the negative x is multiplying by e to the x. So the whole expression on top has e to the x multiplied by it. So it's 2 times e to the 2x times x minus 1 plus c times e to the x. And that's what our expression is. That's the general solution. So y of 0 is equal to 3, we're given. So that's equal to 2 times e to the 2 times 0 minus 1 plus c times e to 0. And so e to the 0 is going to be 1, so that's going to simplify those out pretty quickly. So this is all equal to, so 3 is equal to 2 times e to 0 times negative 1 plus c. Go further, so it's 3 equals 2 times 1 times negative 1 plus c. So 3 is equal to negative 2 plus c, so c equals 5, because we add 2 to both sides. So y of x equals 2 times e to the 2x times x minus 1 plus 5 times e to the x, and that's your solution to the initial value problem. Sorry if it's not the best, most entertaining commentary, but it's pretty, I was very strict about coloring on paper and everything to help guide your eyes sometimes. Oh, this one's a little bit messy, so it's x squared plus 1 times y prime plus 3xy equals 6x, y of 0 equals negative 1. So you have to rewrite this, so it's, you first subtract 3xy, and then we have to divide by x squared plus 1, get y prime by itself. And I put parentheses around to separate y from the a term. So it's negative 3x divided by x squared plus 1 is our a term. Well, even though this does look pretty messy, it doesn't seem, it'll take a little bit more work than our previous ones, but it'll work out. So we do v substitution here. Excuse me. But first we have to do u of x. So basically, u of x equal to, that's why we need v substitution, because it's negative 3 to the 3x by x squared plus 1. So negative, we can get negative 3 out times negative 1, so it's 3 times integral of x divided by x squared plus 1 dx. V equals x squared plus 1. So dv is equal to 2x dx, and you go from here. It's normal substitution to get your integral. And then we plug, once we get 1/2 ln absolute value of x squared plus 1 as our integral, we can substitute that in. So it's 3/2 ln x squared plus 1. Eventually we do get rid of the absolute value because the 3/2 power will cancel it out. Because of how it works. That 2 on the bottom is what canceled it out. So we're doing this to that power. And in the end, the natural log cancels out, so it's just x squared plus 1 raised to the 3/2 power. And that's our integrating factor in purple here. So we do some algebra, and it's x squared plus 1 raised to the 3/2, basically divided by x squared plus 1, which will lead to just it being x squared plus 1 to 1/2. And then of course 6x was also in there from f term. So that's, and it's dx. So we have to integrate this, and we're going to do another substitution, so w. W equals x squared plus 1, and we do the normal process. We put everything in terms of w and integrate in a simpler way. And eventually we do get a thing, so it's in green here, it's 2 times x squared plus 1 raised to the 3/2 plus c. Did an extra showy thing here, I think. And we have y of x equals 2 times this whole thing. But that's the whole expression, a solution. That's the general solution. We have to do the initial value part now. Without the initial value part, it took a while to solve. And we can further simplify this out, so it's 2 plus c times x squared plus 1 to the negative 3/2 power. Because we had the same thing here. So with this a little bit more simplified form, we do y of 0 equals negative 1, which is equal to 2 plus c times, substituting 0 in for t everywhere makes things simpler. This becomes 2 plus c times 1 to the negative 3/2 power, which 1 raised to any power will be 1. So negative 1 is equal to 2 plus c. So c is equal to negative 1 minus 2, which is just negative 3. You plug that in and you have your solution to the initial value problem. Okay, in 16 it's 1 plus t squared times y prime plus 4ty is equal to 1 plus t squared all raised to the negative 2 power, and y of 1 equals 0. So again, we do the same process. We have to isolate y prime by itself. You have a complicated a term and f term. V substitution is needed to get u or t in the end, like to integrate for u to get our integrating factor u or t. But it's nothing that hasn't been seen before. And we even have a cancellation of absolute value in natural logs and stuff. When we get down to it, 1 plus t squared raised to, all squared, times 1 plus t squared to the negative 3 power. We only have 1 plus t squared to the negative 1 power to integrate, basically, dt. Oh, and this is a special one, that's why it's quick. So, you generally not be tested on these inverse. You don't really get tested, at least not when you have to know it off the top of your head. But the inverse trig functions, don't worry too much about them, but this is 1 divided by 1 plus t squared when it's put in the terms like that. And that's that 1 over 1 plus t squared dt is exactly the inverse tangent of t function when you integrate. So inverse tangent of t plus c. You'd have to know that or else you can't do it really. Yeah, so we just keep it as inverse tangent of t divided by 1 plus t squared plus c divided by 1 plus t squared. No, you have to kind of read it to see what's going on in this one. So now we plug in y of 1 equals 0, which is equal to inverse tangent of 1 divided by 1 plus t squared, or 1 plus 1 squared because it's t. And again, result. So we're solving for c here, like usual as initial value problems. Inverse tangent of 1 is exactly just pi fourths. Because that's where sine and cosine, when divided by each other, give you the same thing. Sine divided by cosine gives you. So pi fourths, so and the 2 squared will be just 4 in the end. So we can combine these terms, they both have the same denominator. So pi fourths plus c divided by 4 is equal to 0. So 0 is equal to pi fourths plus c because you multiply by 4. Then you subtract pi fourths to get c equal to negative pi fourths. And you can further simplify this by keeping 4 the denominator down here. So that's y of t. And that's the solution. So in these last three, we're supposed to use the variation of parameters technique to find a general solution of the given differential equations and find a particular solution satisfying a given initial value condition. So the same as before, this time we just have the same basic type problem, we just have to actually use variation of parameters this time. So just a couple of these just to get it, because it's a good thing to know. You have to know how to do it at least. So we're going to have to go through the long process of it. So y prime minus 3y equals 4, y0 equals 2. So initial condition. They always give it as y of something or x of something equals this or that. So before we add 3y to both sides to get, so y prime equals 3y plus 4. So a term is just 3 and f term is 4. Not as relevant in this case because we're not plugging directly into it, but I just state it anyway. If you wanted to do it the other way just to get the same answer and see. So homogeneous, y homogeneous prime equals 3y. Oh yeah, equation 1 is that initial thing, y prime equals 3y plus 4. So we separate variables. We make a dy dt equals 3y. Separate the variables and solve for the integrals on both sides. 3t plus c is equal to l and y. So value again. We go through again, rid of the absolute value of y again. And it's c of t times e to the 3t. That's number 2. We plug 2 into 1. We do a derivative. It's a similar process for a lot of these, at least, you know, like similar to integrating factor, but I just don't like the using c as a function of t because I'm used to that being a pure constant and it weirds me out a little, but that might be why I don't like this method. But it's a method. If you really like it, you can use it. You just have to know how to do both, though. You can use one more than the other, but know how to do both because you can often be tested on using both in the same exam. So when we plug it in, we take the derivative of c of t times e to the 3t. Product rule again, so it's c prime of t times e to the 3t. You know, and then derivative of e to the 3t is just 3 times e to the 3t. And then you multiply by just c of t. And the other side that got plugged in, it's the same as 3 times c of t times e to the 3t, so that gets canceled out on both sides. Then you just have c prime of t eventually equal to 4 times e to the negative 3t. And we integrate both sides. Oh, if I didn't make it obvious, when you just integrate c prime of t dt, it's just c of t. That's what the integral of something is. It's like the integral of f prime of t dt is just f of t. It's a function. That's how it works. So the left-hand side works out. Oh, I included C1 and stuff. I shouldn't put C1, but whatever, we'll just say it. So different constants. But that's the constants, because when you integrate both sides, you get two constants, and of course, constant minus constant will be a constant, and all that stuff. But no, we have to do U substitution. I shouldn't have, well, it doesn't matter since we're not doing U or T here. Because it's e to the negative 3t we have to integrate. Very quick to do. You follow the pathway though. A little bit scrunchy, but. And then we have c of t plus c1 equals 4 times negative 1/3 e to the negative 3t plus c2. We simplify down into equation 3 here. See, because we went, so we have 2 and 3. YH equals c of t times e to the 3t. So y equals negative 4/3 e to negative 3t plus c times e to the 3t, positive 3t, I made sure to emphasize. Because that's how it works. And then we simplify down and we get yt equals negative 4/3 plus c times e to the 3t. Where c is just a constant, and we solve. Y of 0 equals 2, which is equal to negative 4/3 plus c e to the 3 times 0. Just becomes 2 equals negative 4/3 plus c. So c equals 2 plus 4/3, which implies that c equals 10/3. So y at t equals negative 4/3 plus 10/3 times e to the 3t. We have two more like this now. So y prime plus y equals at, e raised to the t power, y of 0 equals 1. So first step, we rewrite it as equation 1 says here y prime equals negative y, or negative 1 times y specified plus e to the t power. So this one's going to be, this one only takes one page to do everything because it's a simpler equation. I need to drink something real quick. Okay, so real quickly, so we have equation 1, which is our equation 1, and we solve for the homogeneous solution, which is just y of it's like before. It's the same process. I don't know how to explain it basically at this point, besides what's on the paper, what else to add. But you do separation of variables, and you go from here. You have a very simple one, same process before. We have c of t times e to the negative t. That's number 2 for homogeneous solution. Because that's the homogeneous component when you're solving for the homogeneous. Very similar process every time. So c of t times e to the negative t equals negative 1 times c of t times e to the negative t plus e to the t power. You do product rule again on the left hand side. And you cancel out a term again. So it's c prime of t times e to the negative t from the product rule because, of course, and you get like basically when you do the product rule, you do c prime of t, just one more time to say it, times e to the negative t because that's the derivative of c a t times e to the negative t, and then you have derivative of e to the negative t times c of t. So negative 1 times e to the negative t times c of t. And that cancels out on the right hand side with negative 1 times c of t times e to the negative t. But that's, and you eventually get to just c prime of t, and this time it's actually very simplistic. So it's c prime of t equals e to the t divided by e to the negative t, which becomes just e of t times e to the t, which is equal to e to the 2t. So we have to integrate both sides. Integrating e to the 2t dt will just end up being e to the 2t divided by 2 plus c2, because it's c of t plus c1. And you can use other constant terms. You can use any other capital letter really, as far as I'm concerned. Whatever convention your professor would use or whatever. But it doesn't matter too much. You know these are constants while c of t is not. But yeah, it's u substitution real quick in black here this time, just to denote it. That gives you e to the 2t divided by 2 plus c2. In the end, it's c of t equals e to the 2t divided by 2 plus c. And that being a constant. And this is number 3. We plug into number 2 here. They get y equals e to the 2t divided by 2 plus c, all times e to the negative t. So then we multiply that in and we simplify down. So y of t equals 1/2 e to the t plus c times e to the negative t. Y of 0 equals 1. Go through all that. You solve basically for the initial value here. And we end up with just 1 equals 1/2 plus c. So it's c equals 1/2 because that's 1 minus 1/2. So simplifying down, we can actually simplify more. So it's 1/2 e to the t plus 1/2 times e to the negative t. That can be further simplified down to just 1/2 times e to the t plus e to the negative t, and that's how I'll leave it. The solution. Let's try. So the last one. X prime minus 2 divided by t squared times x equals 1 divided by t squared. X of 1 equals 0 is our initial condition. X prime equals 2 divided by t squared times x plus 1 over t squared is equation 1 because we have it in our standard form. Homogeneous solution we need, so xh equals 2 divided by t squared times x. So we have to solve this. Dx dt, this time we're doing dx dt. So we solve this, we separate down. Again, it's dx over x equals, this time it's integral of 2 divided by t squared dt, though, for the right hand side. But anyway, you have the natural log of x plus c1 equals 2.
What? Don't do that.
So natural log of x plus c1 equals 2 times integral of t to negative 2 dt. Oh, because we're integrating that, so the left hand side is obvious, it's saying so. But this one is you just have to put into negative, so t to the negative 2 power basically. And that becomes 2 to, the right hand side becomes 2 times t to negative 1 divided by negative 1 because you raise it, but you basically do, it's t to the negative 2 plus 1 divided by negative 2 plus 1 basically. So it's negative 1 and negative 1 there. That makes any sense? Eventually you can simplify further because you have natural log on the left hand side, so you raise both sides to the e power. The absolute is cancelled like normal. We have c of t times e to the negative 2 divided by t power, and the end is our final thing. We have to plug this into 1 here, the first equation. We do our derivative again, product. So this time it's the derivative of negative 2 divided by t is negative 2 times t to the negative 2 power because it's t to the negative 1, so you have we're doing it just to make sure it's clear when we do that product rule. So negative 2 times t to negative 2 power, because we drop it down, so we drop down from when we take the derivative. We take the derivative of that, so so negative 1 is the derivative, basically what's left, because it's like, we drop it down. When you have t squared, it's 2 times t, like that. In this case, it's t to the negative 1, so negative 1 and t to the negative 2 power comes, so it's 1 lower. Because it's negative 1 minus 1 times negative 1, basically the idea. I think that's a Calc 1 skill. Mostly is the exponential add-in, and of course it's muddled with all this stuff, but in the end the work makes sense. You eventually get c prime by itself, so c prime of t equals t to negative 2 power times e to the 2t. When integrating this, we had to do u substitution. And our work eventually produced, and all this pink would eventually produce c of t equals negative 1/2 times e to the 2t plus c. So negative 1/2 times e to the 2t plus c, as I said, we have to plug that into 2 again like before. So yeah, negative 1/2 times e to the 2t divided by t plus c times e to the negative 2 divided by t. Yeah, negative 1/2 times e to the 2t times e to the negative 2t, those will cancel out. That's plus c times e to the negative 2 divided by t. So get our expression, our general solution. Then we solve x of 1 equals 0 equals negative 1/2 plus c times e to the negative 2 divided by 1. So it's 0 equals negative 1/2 plus c times e to the negative 2. We can add 1/2 to both sides, so 1/2 equals c times e to the negative 2. So c equals 1/2 times e squared. As you can see, we might as well just leave it in terms of that. So we use algebra to simplify further when we plug it in. So it's negative 1/2 plus 1/2 e to the 2 minus 2t. 2 divided by t. Because when you multiply them, when it's multiplied together, you keep the operation. So it's 2 and you add them. So 2 plus negative 2 divided by t is just 2 minus 2 divided by t. All raised by the e. And you can further do that by dividing out a 2. So it's 2 times the expression 1 minus 1 divided by t here. And that's all. Yeah, sorry about the gaps and everything, but I need to drink some more before I do any more recording, definitely in the future. And hopefully that explained a lot, though. Basically, it's variation parameters as you do in more substitution methods and everything. While integrating factor, I think, is more streamlined in a lot of ways.